reaction there, carbon 6, hydrogen 12, oxygen 6, plus the oxygen gas there. Now we'll give you carbon dioxide, water, and then 678 kilocal. Hope I get the number right. Yeah, 678. So this would be the reverse reaction. This reaction is an exothermic reaction. Energy is being released. Well, matter of fact, this reaction is happening right now inside your body. And the food that you eat at the breakfast is being converted, well, in the form of glucose there eventually, with the oxygen you breathe in. And everything is being converted back into carbon dioxide and water, and in the meantime releases a lot of energy. You use that energy to support your daily activity. Okay, so the enthalpy involved in a chemical reaction, well, depending on where you see the energy, if it's on the left side of the chemical reaction, endothermic, right side, exothermic. That's how you would determine whether a particular reaction is endothermic or exothermic. Okay, and so in a sense, we can ask you to calculate, say, in this case, if we give you the enthalpy change there, we can also ask you, if you take certain amount of food, in this case, and sucrose, sugar, how much energy can you produce? Now this calculation, well, that's nothing new there, dimensional analysis. What this reaction, what this information giving you here is that if you take sucrose, every mole of sucrose will react with 12 moles of oxygen gas, generating 12 moles of carbon dioxide, 11 moles of water here. Now, when the reaction is finished, enthalpy of the reaction is negative 5,645 kilojoules for the entire reaction. That means each mole of sucrose, when completely reacted, assuming you have enough oxygen there, will release this much energy. Okay. Now, the question is, if you have 5 grams of sucrose, if you burn it completely, how much energy do we have? Well, the first thing that we need to do here is that we need to convert that 5 grams of sugar to moles. Each mole is 342 grams. So that's always the first thing that we need to do. We don't do mass. We can't use mass directly in chemical reaction there, because these numbers, the coefficient, represent the molar ratio. So we want to convert the mass into moles first, and then we need to identify that conversion factor for the energy. Each mole will generate a negative, well, exothermic reaction, 5645 kilojoules. So the mole and mole will cancel out, gram cancel out. That will give you the amount of energy. So in this case, the total amount of energy that can be produced when you burn 5 grams of sugar based on this balanced chemical reaction equation, you're going to end up with releasing 82.5 kilojoules of energy. Okay. So the calculation involved in this particular type of question, really, there's nothing new there. What we need you to be able to recognize here is that this amount, this is actually the energy released from the reaction. If we ask you to complete this chemical reaction with the energy in there, well, you add 5645 kilocalories on the right side. Now, if it's an endothermic process, you put the energy on the left side of the equation. So different ways to represent the amount of energy. When you see delta R, this little r stands for the overall reaction. Delta H is the enthalpy change. Enthalpy change for the reaction, when the reaction is completed, it's a negative number, so it's going to be an exothermic reaction. If it's a positive number, it's an endothermic reaction. Yeah. So that's going to be the type of one type of calculation involved in thermochemistry when we study the energy aspect of the chemical process. So we can try this. We don't have to do it out class, and we have some time here. Okay. So if you have nitrogen monoxide, a gas recently found to be involved in a wide range of bioprocesses there. Well, nitrogen monoxide can react with oxygen, generating nitrogen dioxide. Now, the enthalpy change for the reaction is negative 114.1 kilojoules. So the question is this reaction endothermic or exothermic? Well, you judge that, you answer this question based on the sign here. By convention, endothermic reaction bears enthalpy for enthalpy change for endothermic reaction bears a positive sign. Enthalpy change for the exothermic reaction bears a negative sign. So this is an exothermic reaction. Now the question asks you, how many grams, if you have 1.25 grams of nitrogen monoxide completely converted into nitrogen dioxide, how much energy will be released? Well, that's a dimensional analysis that we should be able to do, okay? Very much similar to what we do with the matter part of the chemical reaction and the balanced chemical reaction equation there. We need to first of all convert that 1.25 gram of nitrogen monoxide into moles, because we know in the balanced chemical reaction equation, every 2 moles of nitrogen monoxide after completely reacting will generate 2 moles of nitrogen dioxide, will also generate 114.1 kilojoules of energy. So if you have 1.25 grams of nitrogen monoxide, and each mole of nitrogen monoxide is equivalent to 30 grams, 16 plus 14. And nitrogen is 14, oxygen is 16. You add them together, 30 grams there. So this will give you the number of moles of nitrogen monoxide. Now we need to identify the proper conversion factor for the energy part of this reaction. Based on the balanced chemical reaction equation, you see every 2 mole of nitrogen monoxide will actually produce 114.1 kilojoule. So here in the conversion factor, you have to factor in the total number of moles of the reactant in the balanced equation, because this amount of energy does not come from 1 mole of nitrogen dioxide. In the balanced equation, we say we need 2 moles of NO, 1 mole of oxygen to generate 2 moles of NO2. The enthalpy change for the overall reaction is based on the balanced equation. So here, this conversion factor, you've got to put that 2, the coefficient, in front of NO into your calculation equation. And if you plug in the number and doing it correctly, and this is an exothermic reaction, the amount of energy will be released is somewhere around 2.38 kilojoules. Negative sign indicates the energy released into the environment, exothermic reaction. Okay, so make sure that it's the positive sign, negative sign, it's not in the pure mathematical sense. There is a negative number, something that's smaller than 0. Well, we're looking for the direction of the energy transfer. Energy is being released into the environment. Okay, that's what's going on there. So that's what the negative sign represents. So this is the things. These are the things that these are the type of calculations. This is one type of calculation, so we need you to be able to do. And there are other things involved in thermochemistry, and we'll look at that in the second learning objective. Okay, I may have a couple more minutes there, and I think I can just well, almost 9 o'clock. We'll go through we'll start our second learning objective, and giving you another example of how do we, when we're looking at a chemical physical process, how do we quantify the amount of heat being transferred? Okay. So the first learning objective, we talked about a lot of definitions there. How do we define work? How do we define energy? How do we define work? What is an endothermic exothermic process? And